In the last lecture we had started our discussion on canonical correlation variables. We had given the basic definitions and also had looked at how to derive the first pair of canonical variables. As we had seen that the first pair of canonical variables are given by the following, that this is given by u1 equal to e1 prime sigma 1 1 to the power minus half times x. So, x is the original set of random variables, x vector is p dimensional, and the second component of the first canonical variable was given by f1 prime sigma 2 2 to the power minus half times this y vector. Now, wherein we had of course defined that x is that p by 1 random vector and y is the q by 1 random vector, is such that we will have the covariance matrix of x and y augmented, that was given by sigma 1 1, sigma 1 2, sigma 2 1 and sigma 2 2. So, this was the variance covariance structure of this x y random vector, and starting from this we were trying to derive the first pair of canonical variables, which we had denoted by u1 and v1. We had derived it of this particular form, wherein of course we have that we consider this matrix which was sigma 1 1 to the power minus half, sigma 1 2, sigma 2 2 inverse, sigma 2 1, sigma 1 1 to the power minus half. So, considering this matrix which is a p by p matrix, and then its eigenvalue eigenvector pairs were denoted as lambda I ei, I equal to 1 to up to p. So, these ei's of course are orthonormalized eigenvectors corresponding to the eigenvalues which are lambda i's, and we use those orthonormalized eigenvalues eigenvectors ei's in framing the first canonical variable u1, which is e1 prime. So, e1 is the orthonormalized eigenvector of this matrix corresponding to the largest eigenvalue, which was lambda 1. So, we had this particular setup that lambda 1 is greater than or equal to lambda 2 is greater than or equal to lambda p. We had also seen that this f1 prime or rather f1 is the eigenvector corresponding to the largest eigenvalue of the matrix, which was sigma 2 2 to the power minus half, sigma 2 1, sigma 1 1 inverse, sigma 1 2, sigma 2 2 to the power minus half. So, and the eigenvalues of both these matrix A transpose and A transpose A of course are same, the non-zero eigenvalues are same, only eigenvalues with 0 multiplicities actually can differ. The multiplicity of 0 eigenvalues in the two matrices can only differ, right. So, what we are first going to take up today is how we can derive the second, third and in general kth canonical variable. So, let us first look at that. So, we are trying to get the derivation of second canonical variables. Now, in the definition of canonical variables, one may recall that we had said that when we are moving on from the first to the second and in general to the kth pair of canonical variables, the second pair of canonical variables will be such that the u2, which will be the first component of the second pair, that will be uncorrelated with the first corresponding first component of the first pair of canonical variables. The second component of the second pair, that is v2, if we had denoted by v2, so that v2 is going to be uncorrelated with the second component of the first pair, that is v1. So, we would require this to follow actually, that the third pair will be uncorrelated with previous two pairs, that is the first and the second pair, and in general for the kth pair we will have the components in the kth pair to be uncorrelated with the previous k minus 1 principal the canonical variables, right. So, we will require that, and we will thus see that u1 and any arbitrary linear combination of x's, say given by a 2 prime x. Now, we may recall that while deriving the first pair of canonical variables, what we had done was to replace this A2 vector by something which was a C vector. So, in terms of that C vector, we can write this as a C2 prime sigma 1 1 to the power minus half times this x, where we had sigma 1 1 to the power plus half times A2, that is equal to C2. So, the C2 vector was the newly defined vector similar to the C1 vector which we had defined for while deriving the first pair of canonical variables, in order to make the denominator to be equal to C prime C or D prime D, as we will see. So, with this definition, this arbitrary linear combination A2 prime x, which is C2 prime sigma 1 1 to the power minus half x, are uncorrelated, are going to be uncorrelated if the covariance between U1 and this C2 prime sigma 1 1 to the power minus half x, which of course is equal to the covariance between, now U1 is given by E1 prime. So, this is this E1 prime sigma 1 1 to the power minus half x, that, and C2 prime, this is C2 prime sigma 1 1 to the power minus half x is equal to 0, right. So, if we have the covariance between U1 and this arbitrary linear combination to be equal to 0, we would require the covariance between these two terms to be equal to 0. That is, if we look at what is the covariance between this random variable and this random variable, it is going to be E1 prime sigma 1 1 to the power minus half times the covariance matrix of x, which is sigma 1 1 into sigma 1 1 to the power minus half times this C2 equal to 0. That is, these terms here sigma 1 1 to the power minus half, sigma 1 1, sigma 1 1 to the power minus half will make this as an identity matrix. So, we would require this E1 prime C2, this to be equal to 0, or in other words, we would require this C2 to be an orthogonal vector, orthogonal to the E1 vector, which is the orthonormalized eigenvector corresponding to the largest eigenvalue lambda 1 of this sigma 1 1 to the power minus half this matrix, right. So, while deriving the second canonical variable, we have to make this C2, we have to choose this C2 vector in such a way that this C2 needs to be orthogonal to E1, the first orthonormalized eigenvector corresponding to the largest eigenvalue. Now, let us look at what is the correlation coefficient between this. Let me take this as first to start with A2 prime x, that is the original linear combination form, that, and B2 prime y. So, we are trying to look at what is that A2 and B2 such that we will have this correlation to be maximized, subject of course to the condition that these A2 and B2 should be such that this A2 prime x will be uncorrelated with U1 and B2 prime y will be uncorrelated with V1, right. So, this correlation is nothing but the covariance between A2 prime x and B2 prime y, this divided by under root of variance of A2 prime x and variance of B2 prime y, right. So, this expression we can write as simply A2 prime sigma 1 2 times this B2 prime, this divided by A2 prime sigma 1 1 A2, this is the first term, and the second term is similar to the first term, B2 prime sigma 2 2 times B2 and whole raised to the power half. So, similar to the derivation of the first pair of canonical variables, what we are going to do is redefine. So, we will take this sigma 1 1 to the power half A2 vector, we will define that as a new vector C2 as we have seen in here. This is the transformation. So, under this transformation and also with sigma 22 to the power half times B2, that to be equal to say a D2 vector, what we will be having in the denominator is that this A2 prime sigma 11 A2 is just equal to C2 prime C2, that multiplied by this D2 prime D2 whole raised to the power half. And here if we have this particular definition, this would further imply that our A2 vector is equal to sigma 11 to the power minus half times C2, and this B2 vector is equal to sigma 22 to the power minus half of the redefined vector, which is D2. So, we can plug in these values here in the numerator of this expression, which will lead us to this C2 prime sigma 11 to the power minus half, that times sigma 12 B2 prime, I am sorry, this is going to be just B2, this is not B2 prime, this is A2 prime sigma 12 B2. So, this B2 is going to be given by this sigma 22 to the power minus half times this D2 vector, right. So, the correlation between these two components is given by this. Now, similar to once again the derivation of the first pair of canonical variables, what we can do is to apply the Cauchy-Schwarz inequality on the numerator of this expression, and we can say that this C2 prime sigma 11 to the power minus half sigma 12 sigma 22 to the power minus half times this D2 vector, that is less than or equal to, we will take this as one vector, say u prime as this vector and v as this vector. So, it will be u prime u to the power half. So, that this is going to be C1 C2 prime sigma 11 to the power minus half sigma 12 sigma 22 to the power minus half, and that also augmented with sigma 22 to the power minus half will give us sigma 22 to the power minus 1, and the transpose of sigma 12, which is sigma 21 sigma 11 to the power minus half times C2, this raised to the power half, and that multiplied by this D2 prime D2, that also raised to the power half, right. Now, we will concentrate on this particular expression here and try to see what can be given as an upper bound of this particular expression. So, in order to get that, we will recall once again a result from matrix theory. Recall that for real symmetric matrix B, say P by P, with eigenvalue eigenvectors pairs with eigenvalue eigenvector pairs as lambda I E I for I equal to 1 to up to p. This is such that of course, lambda 1 is the largest eigenvalue, lambda 1 is greater than or equal to lambda 2 is greater than or equal to lambda p. With such a structure, if we try to look at what is the maximum over x of the expression x prime bx, this divided by x prime x. Now, this x here, if we try to look at all x's such that x is orthogonal to E1, the first orthonormalized eigenvector corresponding to the largest eigenvalue, which is lambda 1, then this maximum over all x's such that they are all orthogonal to this E1 is going to be achieved at the second largest eigenvalue, which is lambda 2, with equality at x equal to C2, right. Now, we had used the first version of this particular result while deriving the first pair of canonical variables, recall that if we do not have this particular condition that we are looking at all x's such that it is orthogonal to E1, if we just look at maximum of this x prime bx by x prime x for all x's, then this is going to be achieved at the largest eigenvalue, which is lambda 1, right, and the equality would be attained at x equal to E1. Now, if we restrict the set of or the region of x's to the situation that all x's which are orthogonal to E1, then what we are going to get is this maximum is going to be attained at the second largest eigenvalues. Now, in general, what also one can say is that maximum x such that x is orthogonal to E1, E2 and Ek. So, E1, E2, Ek are the k orthonormalized eigenvectors corresponding to the k largest eigenvalues of this B matrix. If we now look at all x's such that they are orthogonal to the first k eigenvectors of the quantity, which is same as the previous quantity x prime a x divided by x prime x. Now, this maximum under this condition is going to be attained at the point which is lambda k plus 1. So, it is a nice result with equality here with x equal to E k plus 1. So, this is a standard result anyway in matrix theory. So, we will use this particular result in order to derive the second, third, fourth and in general the kth pair of canonical variables. Now, at what point we are going to use this particular result of eigenvalues? We are going to use that result in this particular expression. Now, let us write this expression. So, this will imply that our C2 prime sigma 1 1 to the power minus half sigma 1 2 sigma 2 2 inverse sigma 2 1 sigma 1 1 to the power minus half this C2, this quantity here will be less than or equal to what? If we are looking at C2, if we are looking at all C's such that that is orthogonal to the first, that is it is uncorrelated with the first canonical variable U1, and we had seen in here in the first discussion that in order to have this C2 should be such that it should be uncorrelated with U1, and the condition is that we have to look at all such C2s which are orthogonal to E1. So, we can apply this particular result here because we are looking at all C2s such that C2 is orthogonal to E1, E1 is the eigenvector corresponding to the matrix defined earlier. So, this is going to be less than or equal to this lambda 2 times C2 prime C2, right. In here the equality will be attained if we take C2 to be equal to E2 with equality here, with equality at C2 equal to the E2 vector, which is the second which is orthonormalized eigenvector corresponding to the second largest eigenvalue. Now, if we have this particular expression, then we can go back to this expression out here and say that this is going to be less than or equal to that particular term. So, this would imply we can actually come to this particular point here and say what is the upper bound of this expression straight away. This would imply that the correlation coefficient between A2 prime x and B2 prime y, this is going to be less than or equal to lambda 2 to the power half C2 prime C2, this to the power half D2 prime D2 to the power half. These halves are coming from the Cauchy-Schwarz inequality of the numerator, and in the denominator we as such have this as C2 prime C2 to the power half and D2 prime D2, this to the power half. So, as we see that the two terms cancel out, and we see that the correlation coefficient between this is bounded by this lambda 2 to the power half. Now, we had denoted these lambda i's as rho I star square. So, we will have the correlation, the maximum correlation between this A2 prime x and B2 prime y, such that the uncorrelatedness with the first canonical variable holds. This is going to be less than or equal to this lambda 2 star, where lambda 2 star square is the eigenvalue of that A transpose matrix, right. And with equality, at what points, what are the points wherein we have applied inequality. So, we, in order to have this equality to hold, we would require this C2 to be equal to E2, and in the previous expression wherein we have got this as the inequality, we would require this D2 vector to be proportional to sigma 2 2 to the power minus half sigma 2 1 sigma 1 1 to the power minus half times C2. So, in all the previous steps, with equality at C2 vector to be equal to E2 vector. Now, C2 vector is in terms of the A2 vector. The relationship between C2 and A2 is this. Thus, we would require this A2 to be sigma 1 1 to the power minus half times E2. That is, we would require this A2 to be sigma 1 1 to the power minus half times E2. So, this is as far as the choice of A2 is concerned, and we would also require the choice of B2, because that is going to play a role in this Cauchy-Schwarz inequality. Here the equality is going to hold if we have, as I said, D2 proportional to this particular vector, which would lead us to the following, that this B2 vector would just be equal to sigma 2 2 to the power minus half times F2 vector. So, this will imply the second canonical variable pairs are going to be given by this E2, which is going to be equal to E2 prime sigma 1 1 to the power minus half times x vector, and V2 vector is going to be equal to F2 prime sigma 2 2 to the power minus half times this y vector. If we choose U1 and U2 to be of this particular form, then not only will these U1, U2 and V2 will be uncorrelated with corresponding U1 and V1, we will have the maximum correlation, of course, being attained. And the second canonical correlation coefficient, is going to be given by rho 2 star. That is, the maximum correlation between this A2 prime x and B2 prime y. This maximum, of course, is such that this uncorrelatedness holds. This is going to be attained at this rho 2 star. One can actually find out what is the correlation between these two variables. This is going to be just the correlation coefficient between the U2 and V2 that we have derived. So, we have been able to thus derive the second pair of canonical variables. We will thus generalize this approach for kth pair of canonical variables. Kth pair of canonical variables, we have this UK to be given by EK prime sigma 1 1 to the power minus half times x, and our VK is going to be 1, that is going to be based on FK prime times sigma 2 2 to the power minus half times this vector y, with the correlation, the kth canonical correlation will be the correlation between UK and VK, which is going to be equal to rho k star, right. So, this is what is the canonical kth canonical correlation coefficient. So, this will be the kth canonical correlation coefficient, and the construction will be similar to the construction of the second pair of canonical variables, that is, this u k will be uncorrelated with u 1 u 2 u k minus 1, and this v k is going to be uncorrelated with v 1 v 2 up to v k minus 1. So, entire that uncorrelatedness structure will still hold, and while deriving this kth pair of canonical variables, we will precisely be using this particular result, that we would at the kth stage would require the C k vector similar to the C 2 vector here. We would require the C k vector corresponding to the kth canonical variable pair to be orthogonal to E 1 E 2 E k, because we would require that particular linear combination, the kth canonical variable, to be uncorrelated with all the previous canonical variables, and hence that particular type of orthogonal structure would be required while deriving the kth pair of canonical variables. Right. So, this is what concludes actually the derivation of all the canonical variable pairs. Now, how many such canonical variables are there? If we look at u 1, u 2, u k, that particular series of canonical variables, then we are going to have p of them, and if we look at this v k, v 1, v 2, v k, so that is going to go up to v q, because we have f q of the eigenvectors present in that A transpose A matrix, which is sigma 2 2 to the power minus half, sigma 2 1, sigma 1 1 to the power minus 1, sigma 1 2, sigma 2 2 to the power minus half. So, these f 1, f 2, f k's are associated orthonormalized eigenvectors of that matrix, whereas these E i's are the orthonormalized eigenvectors of the other matrix, which is p by p, and f k's are the ones which is corresponding to the q by q q by q matrix. Right. Now, let us look at the following result, which is going to summarize the variance covariance structure among these canonical variables. The results are I will just list 4 of those results, which are enough actually to capture the entire structure of the variance covariance structure of this canonical variables. So, we will have, as we have seen, it is trivial actually, that variance of u k is equal to variance of I will just drop this, or maybe just write variance of u k equal to variance of any other v k. This is going to be equal to 1, this they are 1. We will have the covariance between u k and u l. This, since we have, this is true for all k, since we have variances to be equal to 1, the covariance between u k and u l is also equal to the correlation between u k and u l, and they are equal to 0 for every k which is going to be not equal to l. Number 3 is that the covariance between v k and v l, that is equal to the correlation coefficient between v k and v l, that is also going to be equal to 0 for every k which is not equal to l, and also the fourth one, which is covariance between u k and v l, that is going to be equal to the correlation coefficient between u k and v l. This is also equal to 0 for every k which is not equal to l. Right. So, if we are to prove these results, these are simple elementary results actually. Now, in order to prove that the first term, that variance of u k, now u k as we have derived is given by variance of this E k prime sigma 1 1 to the power minus half times x. So, that is going to be equal to E k prime sigma 1 1 to the power minus half covariance matrix of x, which is sigma 1 1 times this sigma 1 1 to the power minus half times E k. So, this will give us an identity matrix. So, this is E k prime E k which is equal to 1. Similarly, exactly in the same way we can prove that variance of this V k for every k, that is also going to be given by. Now, what is going to happen when we are looking at variance of V k? it is going to be variance of this particular term. We will have this as f, we are going to have this as f k prime sigma 2 2 to the power minus half times the covariance matrix of y, which is sigma 2 2 times sigma 2 2 to the power minus half times f k, and that is once again equal to f k prime times f k, that is equal to 1. So, we will have variance of u k and v k for every k to be equal to 1. Let us look at why the covariance between u k and v k. Well, in the way that we have constructed it, they are having the correlations equal to correlation or the covariances to be equal to 0. Now, we can specifically see how that term is equal to 0. This is covariance between E k prime sigma 1 1 to the power minus half times x, and this u l is E l prime sigma 1 1 to the power minus half times x. So, that this term is equal to E k prime, and once again this same matrix is going to come here, which is going to lead us to an identity matrix. So, this is sigma 1 1, this term here, which is multiplied by this E l vector. So, this will be an identity matrix, and what we are left with is simply E k prime E l. Now, since we have E k orthogonal to E k E l, we will have this to be equal to 0 for every k which is not equal to L. Thus, the covariance between u k and v l u l to be will be equal to 0. Similarly, the covariance which is equal to the correlation also, this is going to be given by f k prime f l, and that by orthogonality of f k and f l will be equal to 0 for every k not equal to L. So, we have proved the second part, the first part and the third part. In the fourth part, what we are, this is the third part. In the fourth part, what we are trying to show is that the covariance between u k and v l, what is this equal to? This is equal to covariance between E k prime sigma 1 1 to the power minus half times this x, and V l is going to be given by F l transpose sigma 2 2 to the power minus half times y. So, the covariance between these two would be given by this E k prime sigma 1 1 to the power minus half times covariance matrix of between x and y. So, that is going to be equal to sigma 1 2, and this is followed by the transpose of the coefficient vector. So, that is sigma 2 2 to the power minus half times F l. Right. Now, we had a result which had stated that F l is proportional to, recall, let me put this equation as star, recall that F k or in general F l. So, this F k is proportional to this sigma 2 2 to the power minus half sigma 2 1 times sigma 1 1 to the power minus half times E k. Right. This is what we had seen while deriving the first pair of canonical variables. So, this F k is proportional to this term. So, what we are going to have this one, this basically is going to be a constant times F k vector, because if F k is proportional to sigma 2 2 minus half sigma 2 1 1 1 to the power minus half times E k, we will have the transpose of this to be equal to C times F k prime. So, this will imply that this star expression is going to be equal to a constant C times F k prime F l. Now, this will imply that this product is equal to 0 for every k which is not equal to L. This is so because once again this F k is orthogonal to F l. Now, since we have this, we will have the covariance between u k and V l, which is also equal to the correlation between u k and V l, because these have unit variances u k and V l, and thus we will have this covariance going to be equal to 0 for every k which is not equal to L. For k equal to L, what is going to happen is that this will be equal to 1, and then this will be equal to the constant of proportionality which links this F k and E k. So, we have proved this result also. So, to conclude, we will look at this structure here. The first note is that we will look at the covariance structure of u and v vector. So, we will first look at this covariance between this u vector and the v vector. So, this is going to be given by the blocks which I write in here. So, the first block here is the covariance matrix of u vector. What is that? By the previous result, this is just an IP matrix. Now, the covariance matrix of v vector is nothing but this is an IQ matrix here, and the off diagonal block here, this is what? This is the covariance between u and v, right? The covariance between u and v. So, covariance between u1 and v1, what is that? That is the correlation between u1 and v1. What is that in turn? That is the first canonical correlation. So, that is rho 1 star, rho 2 star, and this is rho p star, up to the point where we can now remember what we had taken was p less than or equal to q, where p is the order of x or the order of u naturally, and q is the order of y, which corresponds to the order also of this v. So, we will have this p of them, which are the p canonical correlation coefficients. And what about the off diagonal entries? These are all zeros, and there are of course more zeros here after this p by p block here, because we can have the correlation between u1 and v p plus 1 up to u1 and v q. So, we will have all these to be equal to 0 augmented, and here we will have just the transpose of this particular matrix. So, this is actually going to be the p by q matrix here, this is going to be the q by p matrix here, and this vector is p by q dimensional random vector. So, its covariance matrix, variance covariance matrix structure is going to be given by this p plus q by p plus q dimensional matrix as in here. In the second note, what we are going to see is that this is canonical correlation coefficients, under a non-singular transformation. So, what we are trying to convey is the following, that we have x as the original set of p dimensional random vector and y, which is q dimensional random vector. We make a transformation from x to ax and from y to say by, wherein we are talking about a and b are non-singular matrices. Now, the point of interest in this note is to look at what is the change in the canonical correlation coefficient, if any, in the transformed set of random vectors. So, instead of considering x and y as the original set of random variable vectors, if we look at ax and by, then what is going to be the corresponding change, if any, in the canonical correlation coefficient. So, these are the two non-singular matrices. Now, if we have this x y, then this has got the covariance structure x and y as we had defined earlier. This is sigma 1 1, sigma 1 2, sigma 2 1 and sigma 2 2. Now, let us see what is the covariance structure of this ax and by. It is easy to see that the covariance structure is going to be A sigma 1 1 A transpose, this is B sigma 2 2 times B transpose, and this is A sigma 1 2 times B transpose, and this is going to be just the transpose of this. So, this is B sigma 2 1 times A transpose, right. So, this variance covariance matrix, which this original variance covariance matrix between x and y, and this is the covariance matrix on the changed random variables. Now, we have this rho 1 star, rho 2 star, rho p star, these are the canonical correlation coefficients, for this xy setup, right. That is what we have derived. Now, we are going to see what are the canonical correlation coefficients if we are going to look at Ax here and By. Now, this rho 1 star square, rho 2 star square, rho p star square are the eigenvalues of the matrix that we had defined earlier, which was sigma 1 1 to the power minus half, sigma 1 2, sigma 2 2 to the power minus half, sigma 2 1, sigma 1 1 to the power minus half. That is, this rho 1 star square, rho 2 star square, rho p, this rho p star square, rho p star square are the roots of this equation, which is sigma 1 1, determinant of sigma 1 1 to the power minus half, sigma 1 2, sigma 2 2 inverse, sigma 2 1, sigma 1 1 to the power minus half minus lambda I, this determinant of this matrix to be equal to 0, just the eigenvalue equation. Now, here what we will do is to pre and post multiply with suitable matrices, such that, let me write those matrices. This is sigma 1 1 to the power half, say here, pre multiplication, sigma 1 1 to the power minus half, sigma 1 2, sigma 2 2 inverse, sigma 2 1, sigma 1 1 to the power minus half, and this gets post multiplied with sigma 1 1 to the power minus half. So, if we do that, we are pre multiplying by determinant of sigma 1 1 to the power half and post multiplying this equation with sigma 1 1 determinant of sigma 1 1 to the power minus half, and hence there is no change in this term here. This still is lambda I, because the multiplication here is sigma 1 1 to the power half into sigma 1 1 to the power minus half, which is still an identity matrix. Now, if we have done that, then this rho 1 star square, rho 2, rho p star square are the roots also of the following equation, which is, this is an identity matrix, sigma 1 2, sigma 2 2 to the power minus 1, sigma 2 1, and this is sigma 1 1 to the power minus 1 minus lambda I equal to 0, this equation, right. Now, what we will do is that we will look at this particular matrix here and see under the non-singular transformation with A and B non-singular matrices what is happening to this particular matrix. So, let us write this matrix here. This is sigma 1 2, sigma 2 2 to the power minus 1, sigma 2 1 times sigma 1 1 to the power minus 1. Now, this under the non-singular transformation set A and B, where is this getting transformed to? Now, sigma 1 2, if we look at this variance covariance matrix structure, this is the variance covariance matrix structure. So, what we can say is that sigma 1 1 is transformed to this, sigma 1 1 is getting to A, sigma 1 to B prime, and so on. So, what we can write in place of sigma 1 2 is that under A B transformation, this is going to A sigma 1 2 B transpose. So, this is corresponding to sigma 1 2. Corresponding to sigma 2 2, what we have is B sigma 2 2 times B transpose whole inverse. Then sigma 2 1 is getting transformed to the transpose of this, which is B sigma 2 1 times A transpose, and sigma 1 1 inverse is what we have as A sigma 1 1 A transpose times whole inverse. We can look at these inverses because all the matrices, this B sigma 2 2 B prime, A sigma 1 1 A prime, all of them are non-singular matrices. So, we can open up and see that this is just equal to A times sigma 1 2 sigma 2 2 inverse times sigma 2 1 times this sigma 1 1 to the power minus 1 times A transpose, right. So, this matrix here, which plays a crucial role in determining what are the canonical correlation coefficients, because this matrix is involved in solving this equation here, and the roots are the canonical correlation coefficients. What we are going to have is that matrix being transformed, this matrix is being transformed here to this matrix. Now, if we look at the roots of this particular matrix, we can also say that further roots of A sigma 1 2 sigma 2 2 inverse sigma 2 1 sigma 1 1 inverse times A transpose, the I should write that the non-zero eigenvalues of further the non-zero eigenvalues of this are same as the non-zero eigenvalues of, if we consider this to be a C matrix, then what we are going to have is that this is going to be a inverse here, because we are looking at the last term here, which is A sigma 1 1 A transpose whole inverse. So, this is a transpose here. So, this matrix is the transpose matrix here. So, the non-zero eigenvalues of this matrix times this matrix is going to be same as the non-zero eigenvalues of this matrix multiplied by this matrix. So, non-zero eigenvalues of this are going to be same as the non-zero eigenvalues of sigma 1 2 sigma 2 2 inverse sigma 2 1 sigma 1 1 inverse. Now, what is this? This is just equal to sigma 1 2 sigma 2 2 inverse sigma 2 1 this. Now, if we look at the previous slide here, these are the eigenvalues are rho 1 star square, rho 2 star square and rho p star square, and hence if the non-zero eigenvalues in the transformed situation are same as that of this particular matrix, what does that imply? This implies that the canonical correlation coefficients are unchanged under this non-singular transformation. This implies that the canonical correlation coefficients under the non-singular transformation transformation AB are unchanged. So, whether we look at the canonical correlation coefficients from the original set of variables x and y, or we look at in the transformed setup with Ax and By, the canonical correlation coefficients in the two sets are going to be precisely the same, right. Now, as a special case of this result, we will take A and B to be the following. If we consider A as the following matrix, which is V 1 1 to the power minus half, wherein V 1 1 is equal to the diagonal matrix of sigma 1 1, and if we choose this B matrix as V 2 2 to the power minus half, wherein we have this V 2 2 to be equal to the diagonal matrix corresponding to sigma 2 2, then if we look at this, then what is the covariance matrix of this Ax matrix? This is Ax vector rather, V 1 1 to the power minus half times x. Similarly, this is x is getting transformed to this Ax, and y is getting transformed to By, which is equal to V 2 2 to the power minus half times y. Now, what is the covariance matrix of this? It would be V 1 1 to the power minus half sigma 1 1 times V 1 1 to the power minus half. What will that be? That will be just the correlation matrix. So, this is the covariance matrix of V 1 1 to the power minus half x, this is going to be V11 to the power minus half times sigma 11 into V11 to the power minus half, which is nothing but the correlation matrix. If we look at the original x vector, that is a correlation matrix, and similarly the covariance matrix between covariant matrix of V22 to the power minus half times y is going to be equal to V22 to the power minus half sigma 22 times V22 to the power minus half, and we will have that as rho 22 matrix, which is the correlation matrix of the y. So, this will imply that the canonical correlation coefficients, let me also write one more step, eigenvalues of rho 11 to the power minus half times rho 12, rho 22 to the power minus half, rho 21 times rho 11 to the power minus half are same as eigenvalues of this sigma 11 to the power minus half, because this is what is that Ax matrix and By matrices eigenvalues, and this is sigma 11 to the power minus half, sigma 12, sigma 22 to the power minus 1, sigma 21, sigma 11 to the power minus half. So, this will imply that the canonical correlation coefficients computed from covariance matrix and correlation matrix are identical, because under the non-singular transformation there is no change as such in the canonical correlation coefficients. If we take this particular non-singular transformation as V11 to the power minus half as A and V22 to the power minus half as B, then the canonical correlation coefficients are also not going to change, and hence whether we look at the sigma matrix and compute the canonical correlation coefficients from the sigma matrix, or we look at the rho matrix, the correlation matrix of x and y, the canonical correlation coefficients are going to be the same, right. Now, we look at the next important result, which is going to look at the following thing, that what is the correlation between the canonical variables and the original set of variables. So, we are now looking at the correlation coefficient between canonical variables and the original variables. So, what we are looking at is these are the canonical variables that we have derived. These are E k prime sigma 11 to the power minus half times x. We have k equal to 1 to up to p. We still work with that particular order, and we have V k. This is given by V k f k times sigma 22 to the power minus half times y, and this k is from 1 to up to q. So, if we look at the u vector, the vector containing all the first components of the canonical variable pairs. So, this is u1, u2 and up. So, this is going to be given by this simple matrix, which is E1 prime, E2 prime, and this is EP prime, that times sigma 11 to the power minus half times x, right. So, if we have this, we just write that as a matrix. This A matrix is different from the previous A matrix, of course. We will write this as Ax, wherein this A is equal to this matrix of eigenvectors E1 prime, E2 prime, EP prime, that multiplied by sigma 11 to the power minus half. So, if we now want to look at, now this is as far as u is concerned. Similarly, one can write this v vector, this is p by 1 vector, this is going to be a q by 1 vector, this is v1, v2 up to vq, and this will be given by f1 prime, f2 prime, fq prime, that times sigma 2 2 to the power minus half times this y vector. Let us denote that by a matrix B times this y vector, wherein B similar to this A is given by f1 prime, f2 prime, fq prime times sigma 2 2 to the power minus half. So, if we have u vector equal to this Ax and v equal to by, it is very simple actually to see that how we are going to compute this covariance between this u vector and the x vector. Now, u vector in terms of the x vector is equal to Ax times this x vector. So, this is simply A times the covariance matrix of x, which is sigma 1 1, and what was A equal to? A was equal to our this E1 transpose, E2 transpose, EP transpose, that times sigma 1 1 to the power minus half. So, that combined with this gives us sigma 1 1 to the power half. So, this just is the covariance matrix between u and x. Now, we can use similarly the covariance matrix of v vector and the y vector. What is that going to turn out? That is going to be given by covariance between by vector and the y vector, which is going to be given by b times sigma 2 2 vector, and that is going to be given by f1 transpose, f2 transpose, fq transpose times sigma 2 2 to the power half. So, we will stop this lecture at this particular point and continue from here.